In this lesson, we'll be learning how to calculate Riemann sums, but when we are given a table of values rather than a graph of the function. So let's recall that estimating the value of a definite integral can be done by finding the sum of a given number of rectangles or trapezoids. We can also calculate Riemann sums and estimate definite integrals when given a table of values for a function. So if we take a look at the sample questions here, we're going to be finding the approximate value of each definite integral by using the indicated Riemann sum. So number 1 asks us to approximate from 0 to 18 using a left Riemann sum and 3 subintervals. So what I'm going to first do in my table of values is I'm going to mark off what each interval would be. So the first is going to be from 0 to 7, then from 7 to 13, and then from 13 to 18. Since this is a Riemann sum and we are using a left Riemann sum in particular, for each of those intervals, when we calculate the area, we're going to be using the leftmost output. So from 0 to 7, the leftmost point is when x is 0, so the leftmost output is going to be 14. From 7 to 13, that would mean I'd be picking 1. And from 13 to 18, I'd be picking -2. So we could say that the definite integral from 0 to 18 of f of x dx is approximately equal to 7 times 14. That's the change in x for the first interval times the output plus 6 times 1 plus 5 times -2, and all of this comes out to be 94. Okay, number 2. We're going to approximate the same idea, the function from 0 to 18, using a right Riemann sum this time and 6 subintervals. So when I break this into 6 sections here, you can see that we're going from consecutive values in the table. So we're going to once again approximate the value of the definite integral. Okay, the first change in x is 3, and then we're going to pick the rightmost point on this one, which is 11. The next change is going to be 4, and we're going to pick the rightmost point, which is 1, plus 2 times 4, plus 4 times -2, plus 2 times -8, and plus 3 times 7. So notice when we are doing a right Riemann sum in the table of values, we end up using all of the rightmost points here, especially when we are using consecutive pieces of the table. So for instance, 0 to 14 and then 3 to 11, 3 and 11. All right, all of this comes out to be -22. Number 3, we're going to approximate from 0 to 24 this time using a midpoint Riemann sum and 4 subintervals. So I'm going to break my domain up into 4 subintervals. For each one, I'm going to be picking the middle y value. So if I look at from 0 to 7, the y value in the middle is at 11. If I look from the interval 7 to 13, 4 is in the middle. For the next set, -8, and the last set, +9. So when we estimate, we're going to get 7 times 11. Remember, this first number is the change in x values, and then the second number is the output. 6 times 4, 5 times -8, and 6 times 9. And all of this will come out to be 115. All right, for number 4, a trapezoidal sum can sometimes be a little bit trickier to do with a table of values because when we have the graph and we're drawing the trapezoid, it's easier to see what the height is or what the bases are. Now we have to almost imagine it. So again, if you need to, go back to the previous lesson to talk about and review how do we draw trapezoids in order to estimate the area under a curve. So using the table, I'm going to break this into 3 subintervals. So that's going to be from 0 to 7, 7 to 13, and 13 to 18. So what each change in x value really represents here is this is really talking about the height of the trapezoid. Whatever the first output is, that's really base 1, and that's going to be base 2. When we do the next trapezoid, it's like that's going to become base 1, and this is base 2, and then it will happen again over here. All right, so the first set is going to be 1/2. The height of the trapezoid is 7 because we're going from 0 to 7. Base 1 plus base 2. Then it's going to be 1/2, 6, 1 plus -2, plus 1/2, 5, -2 plus 7, and all of this comes out to be 62. All right, a couple more. For number 5, we're going to approximate from 0 to 18 using a right Riemann sum and 2 subintervals. Now notice our table of values goes up to 20. So this piece we are going to end up just not using. So sometimes we are only using part of the table of values like we are in this question, not the entire thing. So now we're going to break the pieces we want, so from 0 to 18, into 2 subintervals. So that would be 0 to 9 and then 9 to 18. When we're doing a right Riemann sum, we're going to pick the rightmost output for each interval. So for that first interval, 0 to 9, 9 is the right, and that corresponding output is 4. For the next interval that goes from 9 to 18, the rightmost point occurs at 18, and that output is 7. So when we are approximating this definite integral, the area is going to be 9 times 4. So remember, this is our change of x, and then basically this is our y value. And then we are going to add that to 9 times 7, and this should come out to be 99. All right, for our last one here, we're going to approximate from 7 to 24 using a midpoint Riemann sum and 3 subintervals. So we're only doing from 7 to 24, so I'm just going to cross off this piece of the table of values. We do not need that. And 3 subintervals. So I'm going to do from 7 to 13, 13 to 18, and 18 to 24. All right, so let's set up our calculation here using the midpoint Riemann sum. For the first interval, the change in x values is 6. We're going to pick the middle output, which is 4. From 13 to 18, the change in x values is 5. We're going to pick the middle output, which is -8. And for the last set, the change in x is 6. We're going to pick the middle output, which is 9. And all of this comes out to be 38. Okay. Hopefully this lesson helps you understand how to calculate Riemann sums when given a table of values.